somewhere far beyond the air around Earth, beyond the thin blue glow of the atmosphere, beyond the last drifting grains of dust and ice. There are regions of space that seem almost perfectly empty. No clouds, no oceans, no forests, no cities glowing in the night. No sound travelling through the darkness because there is no air to carry it. No obvious movement, no obvious substance, no familiar thing to point at and say, there it is, just space. A deep, cold, silent stretch between stars where even light may take years, centuries, or longer to cross from one place to another. It is tempting to imagine this emptiness as true nothingness, a blank gap, a cosmic pause, the universe holding its breath between the bright islands of stars and galaxies. But modern physics suggests that this quiet darkness is not quite as empty as it appears, even when every atom is removed, even when the last molecule has been swept away, even when a region contains no ordinary matter at all, something still remains. Fields remain, possibilities remain, the underlying structure of nature remains, and in quantum physics, that remaining nothing becomes one of the strangest and most important ideas science has ever had to describe. Because empty space is not simply a container waiting for things to be placed inside it. It may be part of the story itself. The vacuum can affect atoms. It can shape tiny forces. It may be connected to the expansion of the universe. It sits quietly beneath the behavior of particles, light, matter, and perhaps even the deepest structure of reality, which is quite a lot of responsibility for something that was supposed to be empty. Welcome to the Late Lab. It's lovely to have you here. Before we settle in, where in the world are you watching from tonight? Maybe you're tucked beneath a blanket, half listening with heavy eyes. Maybe you're stretched out on the sofa, letting the room grow quieter around you. Or maybe you're somewhere in between, not quite asleep, not quite awake, drifting comfortably at the edge of thought. Wherever you are, hopefully you're warm, settled, and ready to wander gently into one of the strangest ideas in science. If you enjoy these slow, relaxing journeys through the mysteries of the universe, a like and subscribe really helps this small sleepy channel keep moving through the cosmic dark. And to everyone already subscribed, thank you. Your support is deeply appreciated, even if the universe itself remains rather mysterious about the whole thing. Now, tonight's subject may sound like it should be peaceful, empty space, nothing there, very restful, almost suspiciously restful. But physics, being physics, has found a way to make even nothing complicated, so hopefully this does not keep you too wide awake. But if it does, at least you'll have a better understanding of why the quiet vacuum between stars may contain fields, fluctuations, hidden energy, and some of the deepest unanswered questions in modern science. So let's begin, shall we? What is the quantum mystery of empty space? And why does nothing turn out to be one of the strangest things in the universe? Empty space sounds like the simplest idea in the universe. At first it seems to mean exactly what the words suggest. A place where there is no matter, no air, no dust, no water droplets, no drifting pollen, no warm breath fogging gently in the cold, no chairs, no walls, no planets, no stars passing through that particular patch of darkness. Nothing to touch, nothing to hear, nothing to see. In ordinary life, that is usually good enough. An empty room is empty if nobody is standing in it. An empty glass is empty if there is no tea inside it, which is a small domestic tragedy, but not yet a crisis in physics. An empty box is empty if it has no object rattling around at the bottom. Human beings are very practical about emptiness. If nothing useful, annoying, edible, or suspiciously sticky is present, the space is empty. But science has a habit of making ordinary words more interesting, and sometimes more troublesome. The word empty is one of those words. Imagine taking a chamber in a laboratory and removing the air from it. Pump after pump draws out the molecules. The pressure falls. The chamber becomes quieter in a physical sense, because sound needs particles to carry vibrations. Remove enough air, and sound has almost nothing to travel through. The space inside begins to resemble what most people would call a vacuum. But even this is not true nothingness. The chamber is still sitting on Earth, so it remains inside Earth's gravitational field. The planet is still pulling on every part of the chamber, and the chamber is still part of the curved space-time around Earth. It may be shielded from some influences, but it is not disconnected from the universe. Electromagnetic fields can still exist in and around it. Thermal radiation can still be present. Light can pass through if there is a window. The walls themselves still have temperature, and because they have temperature, they can emit infrared radiation. Even the best vacuum chamber is less like perfect nothingness and more like an extremely tidy room where almost all the furniture has been removed, but the wallpaper, floorboards, heating system and gravity have very much stayed behind. And then, when quantum physics enters the picture, the situation becomes even stranger. Modern physics does not treat empty space as simple blankness. It describes it as something with structure, rules, and measurable behaviour. This is the beginning of the quantum mystery of empty space. The mystery is not that science has failed to notice emptiness. It is almost the opposite. Science has looked at emptiness very carefully and found that the more carefully it is examined, the less empty it seems to be. To understand why, it helps to separate two different ideas. The first is classical emptiness. In the older, everyday classical sense, a region of space is empty if it contains no ordinary matter. No atoms, no molecules, no dust grains, no gas. In this view, space is mostly a stage. Matter moves across it. Light travels through it. Forces may act across it. But the space itself is often imagined as a kind of passive container, like an invisible box that holds whatever the universe happens to place inside. This way of thinking is useful. It works well for many ordinary situations. It helps describe airless environments, vacuum pumps, pressure differences, and the vast gaps between planets and stars. It is also deeply intuitive because it matches the way the world appears. Things exist, and then there are gaps between things. The second idea is quantum emptiness, and this is where the floor begins to creak slightly beneath the familiar picture. In quantum physics, empty space is not a blank void. More precisely, the quantum vacuum is the lowest energy state of quantum fields. That phrase sounds tidy, but it carries an enormous amount of meaning. It does not mean there is absolutely nothing there. It means that the fields described by quantum field theory are in their quietest possible condition, not switched off, not absent, not removed from reality, just in the lowest energy state available to them. Quantum field theory is one of the central frameworks of modern physics. It combines quantum mechanics with special relativity and the concept of fields. In this picture, particles are not little hard beads sitting in emptiness. They are excitations of fields that extend through space-time. The electron is connected to the electron field. The photon is connected to the electromagnetic field. Quarks are connected to quark fields. The particles described by the standard model of particle physics arise from underlying fields that are present throughout the universe. So when a region of space contains no detectable particles, quantum field theory does not say that the fields have vanished. It says that those fields are in their vacuum state. The quietest state is still a state. It is not the same as non-existence. This is a subtle but important shift. Empty space becomes less like an empty stage and more like a silent musical instrument before it is played. Nothing audible is happening, but the structure that allows sound is still there. The strings, the wood, the shape, the tension, The possibility of vibration are all present. The instrument is quiet, not absent. The analogy is not perfect, because quantum fields are not literal strings hidden in the dark, but it points toward the same idea. Quietness is not the same thing as nothingness. This is why the vacuum has measurable properties. In quantum physics, the vacuum can influence atoms. It can affect tiny forces between surfaces. It can appear in calculations of particle behavior. It may even be connected in a still unresolved way to dark energy and the accelerated expansion of the universe. Empty space is not merely a gap between interesting things. It may be one of the interesting things. Laboratories have tested these ideas with astonishing precision. CERN, the European Organisation for Nuclear Research, has explored the behaviour of particles and fields through high-energy collisions, including work connected to the Standard Model and the Higgs field. National laboratories and university research groups have tested quantum field theory through particle accelerators, atomic physics, precision spectroscopy, and measurements of particle properties. Quantum electrodynamics, the quantum field theory of the electromagnetic interaction, has produced some of the most accurate predictions in all of science. That does not mean every mystery is solved. Far from it. The quantum vacuum sits right at the meeting place of some of the greatest successes and deepest puzzles in physics. It belongs to the world of atoms, particles, and fields, where quantum theory works with extraordinary accuracy. But it also touches cosmology, gravity, black holes, and the large-scale behaviour of space-time, where unanswered questions remain. This is what makes empty space so strange. The problem is not simply that it contains hidden stuff. That wording can be misleading, as if the vacuum were packed with tiny invisible marbles waiting to be discovered. The deeper point is that the physical meaning of emptiness changes when the universe is described through quantum fields. A field can be present even when no particle is detected. The lowest energy state can still matter. Nothing, in the strict everyday sense, begins to look like an idea that nature may not actually use. The journey into empty space therefore begins with a very simple question, and slowly becomes a much larger one. What remains when matter is removed? At first, the answer seems to be airless darkness. Then fields remain, space-time remains, radiation may remain, quantum behaviour remains, the vacuum remains. And inside that vacuum are some of the most delicate clues modern physics has found. Vacuum fluctuations, particles and light, the Casimir effect, the strange connection between emptiness and atoms, the mystery of dark energy, and the unresolved problem of how quantum theory and gravity finally fit together. So empty space is not merely the absence of things. It is the quiet background from which many of the deepest questions in physics begin. It looks still. It looks silent. It looks like nothing at all. But in modern science, that silence has structure. For as long as people have wondered about the universe, there has been a very quiet problem sitting underneath nearly everything else. Can true nothingness exist? It sounds like a simple question until it is looked at for more than a few seconds. Nothingness is easy to say, but difficult to imagine. The moment the mind tries to picture it, it tends to put something there. A black space, a silent room, a blank page, a dark sky with no stars. But blackness is still something seen. A room still has walls. A page still has a surface. Even the idea of a location where nothing exists already seems to smuggle in a kind of stage where nothing is happening. So from very early on, thinkers found themselves caught between two possibilities. Either empty space truly exists, and the universe contains gaps between things, or what looks like emptiness is actually filled by something too subtle to notice. In ancient Greece, this became one of the great arguments about nature. The atomists, including Leucippus and Democritus, imagined reality as being made of tiny indivisible pieces of matter moving through empty space. These pieces were called atoms, from the Greek idea of something that could not be cut. Their picture was surprisingly bold. Matter was not continuous all the way down. It came in small units, and those units needed room to move. Without a void, motion itself became difficult to explain. If everything were completely full, with no gaps anywhere, where could anything go? It is a wonderfully practical objection. Even a universe needs a bit of elbow room. But Aristotle disagreed. Aristotle rejected the idea of a true void. To him, nature did not allow empty space in the absolute sense. His physics was very different from modern physics, and many of its details have long since been replaced. But his influence was enormous. For centuries, the idea that nature abhors a vacuum became a powerful way of thinking. Empty space was treated almost as something the natural world resisted. If a gap appeared, matter would rush in to fill it. This was not simply stubbornness or a lack of imagination. In everyday life, empty space really does seem hard to create. Try to pull water up through a straw, and air pressure becomes involved. Turn over a full glass with a card on top, and the surrounding air helps hold the card in place. Remove air from a container, and the atmosphere outside pushes hard against it. The world around us is not a casual nothingness. It is full of air, pressure, weight, temperature, moisture, and invisible motion. The atmosphere is so familiar that it feels almost like absence until it starts doing something dramatic. For a long time, the question of the vacuum remained tangled with philosophy, but in the early modern period it began to move into the laboratory. One of the key figures was Evangelista Torricelli, an Italian physicist and mathematician who had worked as a student and assistant of Galileo Galilei. In 1643, Torricelli performed an experiment with mercury that became one of the great moments in the history of vacuum science. He filled a glass tube with mercury, sealed one end, inverted it into a dish of mercury, and watched as the mercury in the tube fell to a certain height, leaving a space above it. That space became known as the Torricellian vacuum. This was remarkable because it suggested that a region could exist with no ordinary air inside it. The mercury was not being held up because nature hated emptiness, and was panicking in a very philosophical manner. It was being held up by the pressure of the atmosphere pressing on the mercury in the dish. The column of mercury balanced the weight of the air above the outside surface. The experiment did two things at once. It gave science a new way to measure atmospheric pressure, and it made the vacuum less mysterious in a purely philosophical sense. The empty region above the mercury was not perfect nothingness, but it was a real, experimentally produced absence of ordinary air. The vacuum had stepped out of argument and into glassware, which is often how physics likes to enter a room. A few years later, Otto von Guericke, a German scientist and engineer, created one of the most vivid demonstrations of air pressure ever performed. He built hollow metal hemispheres that could be fitted together, then pumped the air out from inside them. Once the air was removed, the surrounding atmosphere pressed the hemispheres together so strongly that teams of horses struggled to pull them apart. These became known as the Magdeburg hemispheres. The lesson was unforgettable. Removing air did not create a harmless emptiness that made no difference. Instead, the absence of air inside the hemispheres allowed the pressure of the outside air to reveal itself with astonishing force. The vacuum itself was not pulling the hemispheres together in the way a rope pulls a cart. The surrounding atmosphere was pushing them from the outside. But the empty space inside made that pressure difference possible. This helped reshape the meaning of emptiness. A vacuum was no longer merely a forbidden philosophical gap. It was a physical condition that could be made, studied, measured, and used. A classical vacuum came to mean a region from which matter had been removed. No ordinary particles, No air molecules bouncing around, no obvious mechanical substance filling the container. In that classical picture, the vacuum was powerful because it clarified what matter and pressure were doing. If gas was present, it pushed. If gas was removed, the pushing changed. The vacuum was defined largely by absence. It was what remained when the familiar material contents had been taken away. This view became extremely useful. It helped scientists understand gases, pressure, pumps, barometers, engines, and the behavior of matter under different conditions. It helped separate the effects of air from the effects of other forces. It made the invisible atmosphere measurable. It turned the seemingly empty air around Earth into something with weight and structure. But it was still incomplete. The classical vacuum treated space mostly as a passive stage. Matter could be removed from it. Objects could move through it. Pressure could differ across it. Light might travel through it, but space itself was not yet understood as something with its own physical richness. It was more like a container after its contents had been poured away. That picture worked well enough until new questions began to gather around it. If light can travel through empty space, what exactly is waving? If electricity and magnetism can act across regions where no matter seems to be present, what carries their influence? If a magnet can pull on a piece of iron through empty air or even through a vacuum, is the space between them truly doing nothing? If the sun can warm Earth across the near vacuum of space, then emptiness cannot simply mean the absence of all physical activity. These questions did not destroy the classical vacuum immediately. Instead, they quietly widened it. They suggested that removing ordinary matter was not the same thing as removing every physical ingredient. A space could be empty of air and still crossed by light, empty of dust and still shaped by gravity, empty of visible substance and still threaded by electric and magnetic effects. The early vacuum experiments were therefore not the final answer to nothingness. They were the first careful clearing of the ground. Torricelli and von Guericke showed that air could be removed, pressure could be measured, and the vacuum could be treated as a real physical condition rather than a purely abstract impossibility. They gave science a way to ask better questions, and once those questions became better, the emptiness became stranger. The classical vacuum was a great discovery, but it was not the end of the story. It showed that space could be emptied of matter. It did not yet show whether space itself was truly empty. Once the vacuum became something that could be made and measured, emptiness changed from a philosophical problem into a physical one. The old question had been whether a true void could exist at all. The newer question was quieter, but even more interesting. If the air is removed and the dust is gone and ordinary matter has been cleared away, is that space really inactive? For a while it was tempting to think so. A vacuum seemed like a cleaned-out container. It had no air molecules bouncing from wall to wall. It had no obvious substance pressing outward. It was a region where matter had been taken away, leaving a kind of physical silence. But nature had already begun offering clues that the silence was not complete. A magnet can pull on a piece of iron without touching it. A charged object can attract or repel another charged object across a gap. A compass needle turns toward Earth's magnetic north, even though there is no visible thread connecting it to the planet. Something seems to reach through space, but not in the ordinary way that a rope reaches, or a hand reaches, or a spoon reaches for the last bit of pudding with suspicious determination. For a long time, action at a distance was deeply unsettling. Isaac Newton's law of gravitation described how masses attract one another across space, and it did so with extraordinary success. But even Newton was cautious about the deeper explanation. A mathematical rule could describe the attraction, but the question of how influence crossed apparently empty space remained difficult. The idea of fields began to change that picture. One of the most important figures in this change was Michael Faraday. Faraday did not begin as a university-trained mathematician. He had worked as a bookbinder's apprentice, educating himself through reading and lectures, which is a pleasing reminder that curiosity is never asked politely for formal permission. Through experiments with electricity and magnetism, Faraday developed a new way of picturing invisible influence. He imagined lines of force stretching through space around magnets and electric charges. These lines of force were not decorative sketches. They were a way of thinking about how electric and magnetic effects filled the surrounding region. Around a magnet, iron filings arranged themselves in curved patterns, tracing the shape of the magnetic field. Around electric charges, forces point in particular directions and have particular strengths. Faraday's insight was that the space around an object was not merely an empty gap across which forces mysteriously jumped. It had a physical condition of its own. This was a profound shift. Instead of asking how one object reached across nothing to tug on another object, the field idea suggested that each object altered the space around it. Another object then responded to the field at its own location. The influence did not need to leap across emptiness like a nervous squirrel. It existed throughout the intervening space. Faraday's lines of force were powerful, but they were also difficult to express in the mathematical language of physics at the time. That next great step came from James Clerk Maxwell. Maxwell took the experimental work of Faraday and others and built it into a unified theory of electricity and magnetism. His electromagnetic theory showed that electric and magnetic fields were not separate curiosities, but deeply connected parts of one system. Maxwell found that a changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field. Even more remarkably, this linked behavior could travel through space as a wave. The electromagnetic field could carry disturbances outward, rippling through a vacuum without needing air, water, or any ordinary material substance to transport it. This was one of the great turning points in physics, because Maxwell's theory also revealed what light is. Light is an electromagnetic wave. The same kind of field behavior that describes electricity and magnetism also describes the visible glow of a candle, the warmth of sunlight, and the invisible signals that later technologies would use for radio communication. Visible light is only one small part of the electromagnetic spectrum. Radio waves are electromagnetic radiation with much longer wavelengths. Microwaves are electromagnetic radiation too. Infrared radiation, which is closely linked to heat, belongs to the same family. Ultraviolet radiation, X-rays and gamma rays are also electromagnetic radiation, with shorter wavelengths and higher energies than visible light. They all differ in wavelength and energy, but they are expressions of the same underlying electromagnetic field. This changed the meaning of empty space dramatically. A region could have no air and no dust, but still contain electromagnetic fields. It could be a vacuum in the classical sense and still be crossed by light. It could be empty of ordinary matter and yet full of waves carrying energy from one place to another. The sunlight crossing the space between the sun and Earth does not need air to travel. It moves through the near vacuum of interplanetary space as electromagnetic radiation. Empty space was no longer simply the absence of substance. It could be the place where fields lived and waves moved. Heinrich Hertz confirmed Maxwell's ideas experimentally in the late 19th century. Hertz generated and detected electromagnetic waves in the laboratory, showing that Maxwell's theory was not only elegant mathematics, but a description of something physically real. The waves Hertz produced were what would later be called radio waves. They behaved as Maxwell's theory predicted, reflecting, refracting, and travelling through space. The invisible had become testable. This is a lovely moment in the story, because it shows physics doing one of its finest tricks, taking something unseen, giving it careful structure, and then proving it by experiment. No one had to see an electromagnetic field in the ordinary sense. Its effects could be measured, its waves could be produced, its behavior could be predicted. That is often how science handles the hidden parts of reality. It does not need them to wave cheerfully from behind a curtain. It needs them to leave reliable evidence. By the end of the 19th century, empty space had become far richer than the old classical vacuum suggested. It was still possible to remove air from a chamber. It was still meaningful to talk about a vacuum as a region with no ordinary matter. But it was no longer reasonable to imagine such a region as completely inactive. Fields could exist there, waves could travel there, energy could pass through it. And yet this was still a classical picture. Maxwell's electromagnetic field was continuous. Its waves could, in principle, have any amount of energy. The field spread smoothly through space, and its changes unfolded according to precise equations. It was a beautiful theory, and it remains one of the foundations of modern physics. But it did not yet contain the strange graininess of quantum behavior. It did not yet say that light could arrive in discrete packets. It did not yet describe particles as excitations of deeper quantum fields. It did not yet suggest that even the lowest energy state of a field might carry unavoidable quantum restlessness. So the discovery of fields made emptiness active, but not yet quantum. Space was no longer a dead stage. It had invisible structure. It could carry light, radio waves, and electromagnetic influence across regions with no air at all. But the energy in those fields still seemed smooth, continuous, and comfortably classical. The vacuum had already become stranger than nothing. It was about to become stranger still. Classical physics had made empty space more interesting by filling it with invisible fields. Light was no longer just a mysterious glow passing through darkness. It had become an electromagnetic wave, a travelling disturbance in electric and magnetic fields, able to cross a vacuum without needing air, water, or any ordinary material to carry it. For a while, this picture seemed beautifully complete. Maxwell's electromagnetic theory described light with extraordinary elegance. It connected electricity, magnetism, and radiation into one grand pattern. It explained why sunlight can travel across the near vacuum between the sun and Earth, why radio waves can move through open space, and why visible light is only one small part of a much larger electromagnetic spectrum. But then light began to misbehave. Not loudly. Light did not kick over the furniture or announce that classical physics was over. It simply refused to fit one very specific problem. The problem was blackbody radiation. A blackbody is an idealized object that absorbs all radiation falling on it, and then emits radiation depending on its temperature. Real objects are not perfect blackbodies, but many can behave close enough to make the idea useful. Heat a piece of metal, and it first glows dull red, then orange, then yellow-white as it gets hotter. The colour changes because the pattern of radiation emitted by the object changes with temperature. Classical physics could describe some of this behaviour, but not all of it. When scientists tried to calculate the full spectrum of radiation from a hot object using the older rules, the predictions went badly wrong at short wavelengths. The theory suggested that the object should emit absurd amounts of high-energy radiation. This became known as the ultraviolet catastrophe, which does sound like a dramatic name for a problem involving hot objects and mathematics, but in fairness, it really was quite catastrophic for the old theory. The world did not behave that way. Hot objects do not pour out infinite ultraviolet energy. Ovens do not become impossible physics disasters every time someone bakes a potato. Something in the theory had to change. In 1900, Max Planck found a way through the problem. He proposed that energy was not exchanged in any completely smooth amount. Instead, it was exchanged in discrete packets. These packets were later called quanta. Planck did not begin by trying to overturn physics. He was trying to solve a very precise problem about heat and radiation. but his solution placed a tiny crack in the classical picture, and that crack would widen into quantum theory. The key idea was that energy exchange came in definite steps. Not any amount at all, but particular allowed amounts, depending on the frequency of the radiation. This did not mean everything suddenly became chunky in the ordinary visual sense. It meant that at a deep level, the exchange of energy had a smallest grain-like structure. That was strange enough. Then Albert Einstein made it stranger. In 1905, Einstein studied the photoelectric effect. This effect happens when light shining on certain materials causes electrons to be emitted from the surface. Classical wave theory suggested that brighter light should gradually give electrons more energy, because brighter light carries more energy overall. But experiments showed something more surprising. The colour, or frequency, of the light mattered in a very specific way. Below a certain frequency, no electrons were emitted, no matter how bright the light was. Above that frequency, electrons could be released almost immediately. Einstein explained this by suggesting that light itself behaved as if its energy came in particle-like packets. These packets were later named photons. Each photon carried energy linked to the light's frequency. A higher frequency photon could give an electron enough energy to escape. A lower frequency photon could not, even if many lower frequency photons were arriving. It was not simply about the total brightness. It was about the energy carried by each individual quantum of light. This was a turning point. Light, which Maxwell had described so powerfully as a wave, now seemed to behave in certain experiments as if it came in packets, not because Maxwell had been foolish. Maxwell's theory was, and still is, extraordinarily successful, but nature was revealing that the classical wave picture was not the whole story. A photon should not be imagined as a tiny glowing bead flying through space like a miniature lantern with ambitions. That picture is tempting, but misleading. In modern physics, a photon is better understood as a quantum excitation associated with the electromagnetic field. It is not a little solid object made of light stuff. It is a particle-like quantum of the field itself. This changed the meaning of empty space again. Before quantum theory, the electromagnetic field could be imagined as a smooth field filling space, with waves moving through it. Empty space could contain these waves, and that was already a major departure from simple nothingness. But once light became quantum, the field itself had to be understood differently. Energy was not always exchanged smoothly. The field could show particle-like behaviour. The vacuum was no longer just the place through which smooth electromagnetic waves travelled. It became the quiet condition of a field that could be excited in discrete quantum ways. The same quantum logic soon reshaped the understanding of atoms. Niels Bohr used quantum ideas to explain why atoms absorb and emit only particular colours of light. In the classical picture, an electron moving around an atomic nucleus might have been expected to radiate energy continuously and spiral inward, which would make stable atoms difficult to explain. Bohr proposed that electrons in atoms occupy specific allowed energy levels. They do not simply have any energy they like. When an electron moves between these levels, an atom can absorb or emit light at a specific frequency. This helped explain the sharp spectral lines seen when atoms give off light. Hydrogen, for example, emits particular colours because its electron changes between particular allowed states. The atom is not a loose little solar system, with an electron wandering wherever it pleases. It is governed by quantum rules, and those rules give matter its stability, structure, and distinct patterns of light. Here, the story of empty space quietly deepens. If light is connected to a quantum field, and atoms absorb and emit light in quantum steps, then the space around atoms cannot be treated as a blank passive nothing. It contains the electromagnetic field in its quantum form. Even when there is no ordinary light passing through, the field itself still has a lowest possible state, and that lowest possible state matters. In classical physics, the lowest energy condition of a field might sound dull. No waves, no motion, nothing happening, very peaceful, almost ready for a nap. But in quantum physics, the lowest energy state of a field is not the same as absolute nothingness. It is the vacuum state, and it belongs to a quantum field with rules, possibilities, and measurable consequences. This is why the birth of quantum light is so important for the mystery of empty space. The story is not only about glowing objects, hot metal, photons, or atoms changing colour. It is about a deeper shift in what physicists meant by a field. Once fields became quantum fields, emptiness became a state of those fields rather than the absence of everything. The vacuum was no longer boring. It had become part of quantum physics. Light had already done something deeply inconvenient for classical physics. It had behaved like a wave spreading through space as electromagnetic radiation, and then, in the photoelectric effect, it had behaved as if its energy arrived in packets. A thing that once seemed comfortably wave-like had acquired particle-like habits. Nature had opened the door to a rather strange thought. Perhaps the categories themselves were not as solid as they looked. For centuries, particles and waves had seemed like very different kinds of thing. A particle was localized. It had a position. It could be imagined as a tiny object moving from one place to another, like a grain of dust, a pebble, or a very small billiard ball that had taken a dramatic interest in physics. A wave was spread out. It could overlap with other waves. It could bend, interfere, and pass through openings in ways that produced patterns rather than simple impacts. Water waves show this beautifully. When two waves meet, they can add together or partly cancel. Sound waves can interfere as well, making some places louder and others quieter. Light, understood as an electromagnetic wave, can also produce interference, forming alternating bright and dark bands when it passes through narrow slits or around edges. These patterns are not what would be expected from tiny pellets simply flying in straight lines. So if light could behave like a wave and also like a particle, a new question appeared. Was this weirdness unique to light, or was matter itself hiding the same double nature? In 1924, Louis de Broglie proposed a remarkable idea. He suggested that matter, not only light, has wave-like properties. Electrons, atoms, and other particles were not merely little solid points travelling along perfectly defined paths. They were associated with waves. This idea was bold because electrons had already been understood as particles with electric charge and mass. They could be accelerated, deflected, and detected. Yet de Broglie argued that they also had a wavelength linked to their motion. This did not mean an electron was secretly a tiny ocean wave. It meant that the behaviour of matter at small scales could not be captured by the old particle picture alone. The electron had a wave-like aspect, and that wave-like aspect could affect where it was likely to be found and how it behaved in experiments. The proof came in the late 1920s. Clinton Davison and Lester Germer, working in the United States, fired electrons at a nickel crystal and found that the electrons scattered in patterns that looked like wave diffraction. The crystal acted a little like a three-dimensional grating, and the outgoing electrons produced results that matched de Broglie's wave idea. Around the same period, George Paget Thomson showed electron diffraction by sending electrons through thin metal films. The patterns again revealed wave-like behaviour. This was deeply important. Electrons were not just being described with poetic language. They were producing interference and diffraction, the kind of behaviour associated with waves. Matter itself had crossed the old boundary. The electron could arrive at a detector as a localized event, but the pattern built up over many events followed wave-like rules. This is one of the places where quantum physics becomes difficult, not because it is vague, but because it is precise in a way everyday intuition does not expect. A quantum object is not simply a tiny ball following a hidden little path that science has not yet managed to spy on. Nor is it simply a spread-out wave in the ordinary classical sense. It is described by a quantum state, and that state allows physicists to calculate probabilities for different measurement outcomes. The mathematical idea often used here is called a probability amplitude. A probability amplitude is not itself an ordinary probability, but it is used to calculate probabilities. These amplitudes can behave in wave-like ways. They can overlap, combine, reinforce, or cancel. That is why quantum objects can produce interference patterns even when detected one at a time. The wave-like part of the description is not merely a physical ripple in some familiar substance. It is part of the deeper rulebook for what can be observed. Two major forms of this rulebook emerged in the 1920s. Erwin Schrödinger developed wave mechanics, using a wave equation to describe how quantum states change. Werner Heisenberg developed matrix mechanics, a very different mathematical approach focused on observable quantities and their relationships. At first, the two methods looked quite unlike each other, but they were soon shown to be equivalent ways of describing the same underlying quantum behavior. Schrödinger's version was easier for many people to picture, because waves feel somewhat familiar. Heisenberg's version was more abstract, but it captured something essential about quantum measurement. Together, these approaches helped build modern quantum mechanics, a theory that does not simply add a few strange decorations to classical physics, but changes the foundations. One of the clearest examples is Heisenberg's uncertainty principle. In everyday life, it seems obvious that an object has both a position and a speed at the same time. A thrown ball is somewhere, and it is moving, in a certain direction at a certain speed. Even if the measurement is poor, the ball itself seems to have definite properties. Quantum physics changes this expectation for very small systems. The uncertainty principle says that certain pairs of properties cannot both be defined with unlimited precision at the same time. The most famous pair is position and momentum, where momentum means the quantity connected to an object's motion. The point is not that measuring devices are clumsy. It is not simply that an electron is so tiny that the act of looking disturbs it, although measurement can indeed affect quantum systems. The deeper point is that quantum states do not contain perfectly sharp values for all such properties at once. The more tightly the position is defined, the less tightly the momentum can be defined, and the other way around. This can sound frustrating, as if nature has hidden the paperwork in a drawer and refuses to hand it over. But the uncertainty principle is not a failure of knowledge in the ordinary sense. It is a defining feature of quantum systems. It tells us that the universe at small scales does not behave like a clockwork machine made of tiny objects with exact paths waiting to be uncovered. That matters enormously for empty space. If quantum physics only changed the behavior of particles, the vacuum might still be imagined as a motionless background where the particles simply appear or disappear. But quantum theory reaches deeper than that. Once fields are treated quantum mechanically, uncertainty applies to the fields as well. A field cannot always be imagined as sitting with perfectly fixed values everywhere, utterly still, like a painted line on a wall. The quantum vacuum is often described as the lowest energy state of a field, but lowest energy does not mean classical stillness. It does not mean a field has been frozen into a perfectly featureless condition. In quantum physics, even the quietest possible state is shaped by uncertainty. The vacuum is not full of ordinary particles in the way a room is full of furniture, but it is also not a dead mathematical blank. This is where the mystery becomes subtle. Empty space is not exciting because it is secretly packed with tiny balls zooming around when no one is looking. That picture is too simple. The deeper idea is that quantum fields have states, and their lowest energy states still obey quantum rules. They can have structure, they can influence measurable effects, they can behave in ways that classical emptiness could never have predicted. The old particle picture gave the universe neat little ingredients. The wave picture gave it spreading patterns. Quantum physics showed that neither picture alone was enough. Matter could diffract. Light could arrive in packets. Electrons could interfere. Probability amplitudes could combine like waves, while measurements still produced definite outcomes. And beneath all of this, empty space quietly changed meaning again. It was no longer only a region with no air, no dust, and no ordinary matter. It was no longer only a place where electromagnetic waves might travel. It was becoming the lowest energy condition of quantum fields, governed by the same strange principles that made particles behave unlike little marbles, and waves behave unlike ordinary ripples. So when modern physics speaks of the vacuum, it is not speaking of a perfectly frozen nothing. It is speaking of a quiet quantum state. Quiet, but not simple. Empty, but not featureless. Still, but not in the old classical sense. The particles were not what they seemed, and neither was the space between them. By the time quantum mechanics had reshaped the meaning of particles, waves, atoms, and light, physics had become both more powerful and more peculiar. It could explain why atoms have structure, why electrons form stable patterns around nuclei, why light arrives in quantum packets, and why matter can behave with wave-like probability. It had opened a doorway into the small-scale world and revealed that nature was not made of tiny clockwork pieces moving along perfectly knowable paths. But there was still a problem. Ordinary quantum mechanics worked beautifully when the number of particles stayed fixed. An electron could be described, an atom could be described, a particle moving through an experiment could be described. But high-energy physics kept showing situations where particles did not politely remain the same number from beginning to end. Particles could be created. Particles could be destroyed. Energy could transform into matter, and matter could transform into other forms of energy. The universe, it turned out, was not especially committed to keeping the cast list unchanged. This was not a small detail. In the world of atoms and particle collisions, creation and destruction are not optional decorations, they are central behaviors. When light of high enough energy interacts with matter, new particles can appear. When unstable particles decay, they vanish and leave other particles behind. In high-energy collisions, the particles coming out of an event can be completely different from the particles that went in. A theory that only describes a fixed number of particles is like a theatre review that assumes no one ever enters or exits the stage. It can still say useful things, but eventually the plot gets away from it. There was also another deep issue. Quantum mechanics had to be brought together with special relativity, Albert Einstein's theory from 1905, which showed that space and time are linked, and that the speed of light in vacuum is the universal speed limit for causal influence. At small scales and high energies, quantum behavior and relativity both matter. A complete theory needed to respect the rules of quantum physics without breaking the rules of space-time. This is where quantum field theory began to emerge. Quantum field theory is the framework that combines quantum mechanics, special relativity, and fields. It takes the field idea from Faraday and Maxwell, where invisible physical quantities extend through space, and gives it quantum rules. It also allows particles to be created and destroyed, because particles are no longer treated as the most basic ingredients. Instead, particles are understood as excitations of fields. That word excitation is important. A field can be in a quiet state, or it can be stirred into a state that appears as a particle. The electromagnetic field, when excited in the right way, gives rise to photons. The electron field, when excited in the right way, gives rise to electrons. Other fields give rise to other particles. In this view, a particle is not a tiny independent bead sitting inside empty space. It is a localized quantum disturbance of an underlying field. This changes the feeling of reality. The field is not something the particle carries around with it like luggage. The field is the deeper thing. The particle is a particular way the field shows itself. It is a little like how a ripple is not separate from water. The ripple is a pattern in the water. Of course, quantum fields are not literal water, and particles are not ordinary ripples, but the comparison helps soften the idea. The particle is not placed on top of reality. It is a behavior of reality. One of the crucial figures in this development was Paul Dirac. Dirac wanted a quantum theory of the electron that also obeyed special relativity. In 1928, he developed a relativistic equation for the electron. It was one of the most remarkable achievements in theoretical physics, not only because it described electron behavior in a deeper way, but because it seemed to imply something unexpected. Dirac's equation predicted the existence of antimatter. At first, this sounded almost too strange. The mathematics suggested a counterpart to the electron with the same mass but opposite electric charge. This particle would later be called the positron. It was not added because someone fancied a more dramatic universe. It appeared naturally from the attempt to unite quantum mechanics with relativity. Then, in 1932, Carl Anderson observed the positron in cosmic rays. Cosmic rays are high-energy particles from space that strike Earth's atmosphere and can produce showers of secondary particles. Anderson studied tracks left by these particles in a cloud chamber, where charged particles leave visible trails as they move through a supersaturated vapor. The track of the positron showed the behavior expected from a particle like the electron but with positive charge. Antimatter had moved from mathematics into observation. This was a profound moment. It showed that the strange implications of relativistic quantum theory were not just abstract symbols wandering around on a physicist's notebook looking important. They corresponded to real things nature could produce. The vacuum, particles and fields were beginning to belong to a much larger story than the old picture of tiny objects moving through empty space. Quantum field theory gave physics the language it needed. It allowed the number of particles to change. It made sense of particle creation and annihilation. It explained how high-energy processes could transform one kind of particle state into another. It treated particles as excitations of fields that extend throughout space-time. And this is where the quantum mystery of empty space becomes much clearer and much stranger. In quantum field theory, fields are not optional additions to space. They are fundamental ingredients of the physical description. The electron field exists throughout space-time. The electromagnetic field exists throughout space-time. Quark fields, neutrino fields, and other fields associated with the particles of the Standard Model are also part of the structure. The Standard Model of particle physics is built from these quantum fields and the interactions between them. So what is empty space in this picture? It is not a region where the fields have disappeared. It is not a place where the universe has been scraped clean down to absolute nothing. Empty space is the state in which the fields have no ordinary particles present. The fields remain. Their lowest energy condition remains. The rules that allow particles to appear as excitations remain. This is a subtle but enormous difference from the older classical vacuum. In the classical vacuum, emptiness meant matter had been removed. In the quantum field view, even after ordinary matter is removed, the fields are still there. A vacuum is not the absence of the physical system. It is a particular state of the physical system. That is why empty space cannot be imagined as a lifeless blank. It is quieter than a region filled with particles, radiation, atoms, or dust. It may contain no detectable matter at all, but it is not empty of the fields from which detectable particles arise. Those fields are woven into the description of the universe itself. This does not mean empty space is secretly crowded in an everyday sense. It is not like a room filled with invisible bees, which is probably for the best. The vacuum is not packed with ordinary particles hiding from view. The important point is more precise. The vacuum is the lowest energy state of quantum fields, and those fields are the underlying ingredients from which particles emerge. A particle can be created because a field can be excited. A particle can be destroyed because an excitation can be removed or transformed. Matter and radiation are not separate little things sprinkled into a dead void. They are patterns and excitations in fields that fill space-time. So the birth of quantum field theory changed the question of emptiness at its root. The deepest issue was no longer only whether space could be emptied of air, dust, or atoms. It was whether empty space itself should be understood as a physical state. And modern physics answers yes. Empty space is empty of ordinary particles, but it is not empty of fields. By this point, empty space has stopped behaving like a simple blank. It began as the absence of matter. Then it became a vacuum in the classical sense, a region with air removed. Then fields entered the story, and space could be crossed by invisible electric and magnetic influences. Then quantum theory arrived, and those fields were no longer smooth classical substances, but quantum systems with their own rules. So when modern physics talks about the vacuum, it is no longer talking about pure nothingness. The quantum vacuum is the lowest energy state of a quantum field system. That sounds neat and final, but it is worth slowing down around the phrase lowest energy state. It does not mean a state where absolutely nothing exists. It does not mean a place where reality has been switched off. It does not mean the universe has found a little patch of non-existence and politely labelled it empty. It means that the fields in that region are in the quietest state available to them. Quietest is not the same as absent. A simple way to picture this, very loosely, is to imagine the surface of a dark sea at night. From far away it might look still. No storm, no crashing waves, no white spray. Just a broad, quiet surface under a black sky. But look more closely, and the sea is not mathematically flat. It has tiny movements, subtle swells, small disturbances that never quite vanish. The image is useful only up to a point, because quantum fields are not literal water. There is no hidden ocean sloshing around behind the stars, but the comparison helps with one idea. The quietest possible state is not necessarily a perfectly dead state. In classical physics, the lowest energy state of something can often be imagined as complete stillness. A pendulum hanging straight down is at rest. A ball lying at the bottom of a bowl has reached its lowest position. A stretched string, if it is not vibrating, seems to have no motion at all. Classical intuition likes this. It gives the mind a tidy little picture. When energy is removed, activity fades away, and eventually everything rests. Quantum physics is not so tidy. In quantum systems, there is a limit to how completely certain properties can be pinned down. This is connected to Heisenberg's uncertainty principle. For particles, it means that pairs of properties such as position and momentum cannot both be defined with unlimited precision at the same time. For fields, the idea becomes deeper and more abstract, but the spirit remains similar. A quantum field cannot always be treated as though it has one perfectly fixed value and one perfectly fixed rate of change everywhere all at once. Because of this, the lowest energy state of a quantum system may still have irreducible quantum behavior. Irreducible here simply means it cannot be removed by better engineering. Colder temperatures, sharper instruments, or a sternly worded complaint to nature. It is built into the structure of the theory. This leads to the idea of zero-point energy. Zero-point energy is the minimum energy a quantum system can have, and that minimum does not always have to be zero. A familiar example often used in physics is the quantum harmonic oscillator, a basic model of a system that can vibrate. In classical physics, an oscillator could sit perfectly still at its lowest point with no energy of motion. In quantum physics, the lowest possible state still has a minimum amount of energy, not because someone forgot to turn it off, but because the quantum rules do not allow the system to be perfectly motionless in the classical sense. This is one of the reasons the vacuum is so strange. If quantum fields fill space-time, and each field has a lowest energy state, then empty space is not the absence of the system. It is the system in its quietest possible condition, and that quiet condition can still have quantum properties. This is also where popular language can become a bit slippery. People often say that in the quantum vacuum particles are constantly popping in and out of existence. As a quick image, it sounds lively and memorable. It gives empty space a little sparkle, like reality is quietly making popcorn in the dark. But taken too literally, it can be misleading. It can make it sound as though tiny ordinary particles are physically appearing in space, hanging around for an instant, and then vanishing like shy fireflies. That is not the careful meaning used in quantum field theory. In many calculations, physicists use the language of virtual particles, especially in quantum electrodynamics and other quantum field theories. Virtual particles are extremely useful mathematical elements in those calculations, but they are not the same as real detectable particles flying through space. A real particle can be detected as an actual excitation of a field. It can carry energy and momentum in a way that leaves a clear physical trace. A virtual particle, by contrast, is part of the internal bookkeeping of an interaction in the mathematical description. The phrase is useful, but if it is pictured too literally, it can cause more confusion than clarity. Vacuum fluctuations are better understood as fluctuations in quantum fields and as measurable effects that appear in the behavior of quantum systems. They are not best imagined as a swarm of tiny solid things flickering into reality like sparks in empty air. The vacuum is subtler than that, less cartoonish, but far more interesting. This does not make vacuum fluctuations unreal. It means they have to be understood carefully. Quantum fields have behavior even in their lowest energy state, and that behavior can show up in physical effects. It can influence how particles interact. It can affect the energy levels of atoms. It can contribute to tiny forces between closely spaced surfaces. And on the larger scales, questions about vacuum energy may be connected to cosmology, including the expansion of the universe. So the vacuum is not empty in the everyday sense, but it is also not filled in the everyday sense. It is not a hidden gas. It is not a mist. It is not a foam of miniature planets, particles, or glowing beads. It is the lowest energy state of quantum fields, and quantum fields do not behave like familiar objects. That is the delicate point. The vacuum is quiet, but not meaningless. It is low in energy, but not classically dead. It contains no ordinary particles, yet it belongs to fields that can produce particles when excited. It is the background state beneath matter, light, and interaction, but it is not merely a passive background. Even at its most silent, empty space can still help shape what happens, and that is why the lowest energy state of the universe may turn out to be one of the most physically important states of all. Vacuum fluctuations are one of those ideas in quantum physics that sound almost designed to be misunderstood. The phrase itself is wonderfully tempting. It suggests empty space trembling with hidden activity, as if the vacuum is a dark room full of tiny invisible sparks, appearing and disappearing before anything has time to notice. It gives the impression of a universe that is never quite still, even in its quietest places. And in a careful sense, that is true, but in an overly simple sense, it can quickly become misleading. The quantum vacuum is not a normal empty container secretly packed with tiny particles. It is not a cosmic snow globe full of microscopic beads flickering in and out of view. It is the lowest energy state of quantum fields. Those fields are not ordinary substances, but fundamental ingredients in the modern description of particles and forces. And because they are quantum fields, they cannot be treated like perfectly smooth classical fields with perfectly definite values everywhere. In classical physics, a field can often be imagined as having a precise value at each point in space. The electric field here has this strength. The magnetic field there points in that direction. In principle, the field can be pictured as something cleanly defined across a region, like invisible weather mapped over space. That picture is useful, and for many everyday purposes it works beautifully. Quantum fields behave differently. They are still fields, but they obey the rules of quantum theory. That means the field and its possible changes cannot always be assigned perfectly sharp values in the same way a classical field can. The uncertainty principle, developed by Werner Heisenberg, is usually introduced using particles, especially position and momentum. But the same deeper idea also applies to fields. Certain properties of a quantum field cannot both be fixed with unlimited precision at the same time. This is one reason the vacuum cannot be imagined as a field sitting perfectly flat and frozen everywhere, like a painted line that never moves. The lowest energy state is not a state of absolute mathematical deadness. It is the quietest possible state allowed by the quantum rules, and those rules include unavoidable uncertainty. This is where vacuum fluctuations enter the story. A vacuum fluctuation does not mean a tiny ordinary particle definitely appears at a specific place, has a tiny adventure, and then disappears before being caught. That image is common, and it can be helpful as a rough doorway into the idea, but it should not be mistaken for the careful physics. Fluctuations are better understood as the unavoidable quantum behavior of fields in their lowest energy state, and as effects that appear in the mathematics and measurements of quantum field theory. The phrase virtual particles adds another layer of confusion. In quantum field theory, virtual particles are used in calculations, especially when physicists describe interactions between real particles. They appear inside mathematical diagrams and expressions, helping calculate how fields interact and how measurable outcomes arise. They're extremely useful, but they're not the same as real particles. A real particle can be detected. It can arrive in a detector, leave a track, deposit energy, or produce some physical trace that can be measured directly. A virtual particle is not a little object flying around in the same ordinary sense. It is part of the internal structure of a calculation. It is a way of organizing the mathematics of interactions between quantum fields. Treating virtual particles as if they are always tiny real things briefly borrowing existence can make the vacuum sound more dramatic than it needs to be. And the real story is already dramatic enough in a very quiet way. The theory that handles these ideas with extraordinary success is quantum electrodynamics, the quantum field theory of the electromagnetic interaction. It describes how charged particles, such as electrons, interact with the electromagnetic field. It is one of the most precisely tested theories in science. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga played central roles in developing modern quantum electrodynamics after earlier foundations had been laid. They created powerful methods for dealing with the complicated interactions between charged particles and the electromagnetic field. Feynman's diagrams became especially famous because they gave physicists a visual and calculational way to organize interactions. Schwinger developed a highly precise mathematical approach. Tomonaga independently built a relativistic formulation that handled quantum fields consistently. Freeman Dyson then helped show how these different approaches were connected. He demonstrated that the methods used by Feynman, Schwinger, and Tomonaga were not separate islands, but different routes through the same powerful landscape. This helped make quantum electrodynamics a central tool of modern physics. One reason physicists trust quantum electrodynamics so deeply is its precision. It predicts certain measurable properties of particles with astonishing accuracy. A famous example is the electron's magnetic moment, which describes how the electron behaves like a tiny magnetic object. The measured value and the theoretical prediction agree to an extraordinary degree. The details are complex and the exact numbers do not need to be recited like a bedtime phone book, but the agreement is one of the great triumphs of modern science. This precision matters because it shows that the vacuum effects in the theory are not just decorative language. The calculations include contributions from quantum fields, including effects associated with the vacuum, and those calculations match experiments with remarkable success. The vacuum may sound abstract, but its fingerprints appear in real measurements. So vacuum fluctuations should be treated with both wonder and caution. They are not magic. They are not proof that anything can appear from nothing in the everyday sense. They are not a shortcut to unlimited energy. They are a feature of quantum fields, described by a theory that has been tested with extraordinary care. Empty space, in this view, is not a blank sheet. It is the quiet state of fields that cannot be made perfectly classical, perfectly motionless, or perfectly featureless. Its behavior is subtle, but not imaginary. It does not shout. It does not sparkle in the ordinary darkness. It does not reveal itself like dust in a sunbeam. It waits inside the mathematics, and then, very softly, it shows up in the measurements. The quantum vacuum is a difficult idea to hold in the mind, partly because it is not something that can be seen directly. It does not glow in the dark. It does not sit in a jar looking mysterious. It does not announce itself with a tiny sign saying, "Here lies the lowest energy state of quantum fields. Please do not poke." But physics becomes especially convincing when an invisible idea produces a measurable effect. One of the clearest examples is the Casimir effect. It is often introduced as evidence that the quantum vacuum is not merely an empty absence, but a physical state with consequences. Like many famous ideas in physics, it can sound almost magical when described too quickly. Two metal plates are placed extremely close together in empty space, and somehow, the emptiness between them helps create a force. That sounds like the beginning of either a great scientific discovery or a very suspicious machine being sold online with dramatic music. The real effect is more careful, more subtle, and far more interesting. In 1948, the Dutch physicist Hendrik Casimir predicted that two closely spaced conducting plates in a vacuum should experience a tiny attractive force. The plates had to be very close together, much closer than anything encountered in ordinary daily life. At everyday distances, the effect is so small that it disappears beneath all the louder forces and messier details of the world. But at tiny separations where quantum field effects matter, the vacuum itself can contribute in a measurable way. To understand the basic idea, it helps to return to the electromagnetic field. In classical physics, light is an electromagnetic wave. In quantum field theory, the electromagnetic field is a quantum field, and photons are its excitations. Even when no ordinary photons are present, the field still has a vacuum state. That vacuum state is not a perfectly dead blank. It is shaped by quantum rules. Now imagine two extremely flat conducting plates facing one another across a very small gap. Conducting plates affect electromagnetic fields because electric charges in the material respond to those fields. The plates impose boundary conditions, meaning they restrict the kinds of electromagnetic field patterns that can exist between them. A simple way to picture this is to think of a musical instrument, such as a flute or a guitar string. Only certain notes fit naturally inside the instrument's physical shape. The shape restricts the allowed vibrations. The same rough idea applies here, although the real physics is not music and the plates are not politely humming. Between the plates, only certain electromagnetic field modes can fit. Outside the plates, more modes are available. A mode is a possible pattern of the field, a way the field can vary in space and time. Because the space between the plates is restricted, the vacuum state of the electromagnetic field between them is slightly different from the vacuum state outside them. That difference matters. The allowed field modes between the plates and the allowed field modes outside the plates do not balance in quite the same way. The result is a tiny net attractive force pushing the plates together. It is not that the vacuum is grabbing the plates with little invisible hands. It is not that particles are blasting around like microscopic hailstones and shoving the plates inward in a simple mechanical sense. The careful explanation comes from the way quantum fields behave under the boundary conditions set by the plates. The force is real, but tiny. It becomes noticeable only when the separation between the plates is extremely small, often described on the scale of nanometers or micrometers. A nanometer is about a billionth of a meter. A micrometer is about a millionth of a meter. These are not kitchen table distances. They belong to the world of precision instruments, clean surfaces, careful measurements, and the kind of laboratory patience that deserves a comfortable chair and possibly a biscuit. The Casimir effect has been measured in laboratory settings. Experiments have used very precise equipment to detect the tiny forces between closely spaced surfaces. In practice, real experiments are more complicated than the simplest textbook picture. Perfectly flat, perfectly conducting plates are an idealization. Real materials have surface roughness, finite conductivity, temperature effects, and other practical details. Scientists must account for these carefully to compare measurements with theory. This is important because the Casimir effect is not a loose philosophical claim. It is not just a nice metaphor for the vacuum being lively. It is a physical effect, predicted from quantum field theory and studied experimentally. It shows that the vacuum state of a field can influence matter under specific conditions, but it also needs to be handled honestly. The Casimir effect is sometimes oversold. It can be described as if it proves that empty space is full of limitless energy, waiting to be harvested, like a cosmic battery with the lid left off. That is not what the effect shows. The force between plates is extremely small, and extracting usable energy from the vacuum in some unlimited science fiction sense is not supported by the Casimir effect. It is not a hidden power source for starships, household appliances, or suspiciously confident internet diagrams. The effect does not say that energy can be pulled freely from nothing. It says that the quantum vacuum has measurable properties, and that when physical boundaries restrict field modes, forces can arise. That is already remarkable enough without adding extra drama. Physics does not need to be exaggerated to be astonishing. It is doing quite well on its own. The Casimir effect also helps correct a common misunderstanding about empty space. If emptiness were simply absolute nothingness, changing the shape of a region would not matter. There would be no field modes to restrict, no vacuum state to compare, no physical difference between the region inside the plates and the region outside. But in quantum field theory, the vacuum belongs to fields, and fields respond to boundaries. The geometry and material conditions of a region can affect the allowed behavior of those fields. This is a very different kind of emptiness from the classical vacuum. In the classical picture, a vacuum chamber is empty if its air is removed. That remains true and useful, but the Casimir effect reveals a deeper layer. Even when ordinary matter is gone, even when no dust or gas fills the gap, the quantum electromagnetic field still has a vacuum state, and that vacuum state can be shaped by the presence of nearby conducting surfaces. The word pushes can be slightly misleading if taken too literally, because the Casimir force is usually described as an attraction between the plates, but in practical language the plates are pressed together by a difference in field conditions. The apparently empty region between them is part of the physical explanation. Empty space, under careful conditions, helps produce a real force. That is why the Casimir effect has become such an important example. It gives the quantum vacuum a kind of experimental seriousness. It takes the abstract idea of lowest energy field states and connects it to something that can be measured. It shows that the vacuum is not merely an absence in the story, but a participant in the behaviour of matter and fields. There is a calm strangeness in that. Two plates sit in a vacuum. Nothing visible fills the narrow gap between them. No air pushes from inside. No tiny mechanical spring connects them, and yet the rules of the electromagnetic field, shaped by quantum theory and by the plates themselves, create a force so delicate that it almost seems like a whisper from the structure of space, not magic, not free energy, not a gateway to easy cosmic machinery. Just empty space, proving once again that it is not quite empty. The Casimir effect shows that the quantum vacuum can matter between carefully arranged surfaces, but the vacuum does not only reveal itself in tiny forces between metal plates, its influence can appear in places that seem even quieter and more familiar, inside atoms. An atom can look, at first glance, like the sort of thing that should be neatly self-contained. A nucleus sits at the centre. Electrons occupy allowed states around it. Light is absorbed or emitted when electrons move between energy levels. It is tempting to imagine the atom as a tiny private machine, sealed off from the emptiness around it, running according to its own internal rules. But atoms are not isolated clockwork systems floating in a perfectly blank background. They belong to quantum fields. Their electrons interact with the electromagnetic field, and even when no ordinary light is shining on an atom, the quantum vacuum of that field still plays a subtle role. One of the most important clues came from the Lamb shift. In 1947, Willis Lamb and Robert Rutherford measured a tiny energy difference in hydrogen. Hydrogen is the simplest atom, with one proton and one electron, which makes it one of the cleanest testing grounds in physics. Because it is so simple, physicists can calculate its behaviour with great precision. If a theory cannot handle hydrogen, it is probably going to have a difficult afternoon with anything more complicated. Before the Lamb and Rutherford measurement, the relativistic quantum theory developed from Paul Dirac's work predicted that certain energy states in hydrogen should have exactly the same energy. These states had different internal quantum descriptions, but according to the earlier theory, they should have matched. Lamb and Rutherford found that they did not. There was a small difference, very small. But physics has a habit of treating small differences with enormous suspicion, and in this case the suspicion was justified. The measured difference became known as the Lamb shift. At first it may sound like a minor correction, the sort of delicate adjustment that only a specialist could love. But the Lamb shift was not just a tiny detail. It was evidence that the existing theory was incomplete. The electron in hydrogen could not be fully understood as though it were moving around the proton in isolation, with only a simple electromagnetic attraction between them. The electron was also interacting with the quantum electromagnetic field, including the vacuum state of that field. This helped reveal the need for quantum electrodynamics, the quantum field theory of the electromagnetic interaction. Quantum electrodynamics describes how charged particles such as electrons interact with the electromagnetic field. It treats light and matter through the language of quantum fields, not merely through fixed particles and smooth classical waves. The Lamb shift became one of the early triumphs that showed this more refined theory was necessary. The key idea is subtle. An electron in an atom is not a tiny planet orbiting a nucleus along a neat little track. It occupies a quantum state, described by a probability distribution. That state determines where the electron is likely to be found and how it can interact. Around and within that atom is the electromagnetic field, and in quantum electrodynamics, even the vacuum state of this field has effects. The electron's interaction with the quantum vacuum slightly shifts its energy levels. This does not mean the atom is being battered by little invisible particles in a simple mechanical way. The careful explanation comes from quantum field theory. The electron interacts with fluctuations of the electromagnetic field and also with its own field in ways that require careful mathematical treatment. These interactions alter the electron's energy very slightly. Slightly in this case is the important word. The effect is not large enough to notice in ordinary life. Hydrogen atoms are not wandering around looking unsettled because their energy levels have been gently nudged by the vacuum. They remain extremely reliable little things, which is considerate of them. But the Lamb shift matters because it is measurable and because it agrees with the deeper theory. Hans Bethe made an early theoretical calculation of the Lamb shift in 1947, shortly after Lamb and Rutherford's result was presented. Bethe's calculation was not the final form of modern quantum electrodynamics, but it showed that the energy difference could be understood as an effect of the electron interacting with the quantized electromagnetic field. It helped point the way toward the rapid development of the full theory. This period was one of the most important in 20th century physics. Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson helped build the modern structure of quantum electrodynamics, developing methods that could calculate electromagnetic interactions with extraordinary precision. The Lamb shift became one of the key experimental tests that the theory had to explain. Along with measurements of the electron's magnetic moment, it showed that quantum electrodynamics was not just philosophically interesting, but experimentally powerful. What makes the Lamb shift especially beautiful is that it reveals the quantum vacuum in a very intimate setting. The Casimir effect shows the vacuum influencing a force between surfaces. The Lamb shift shows the vacuum influencing the inner energy structure of an atom. Empty space is not only relevant in wide cosmic gaps or carefully engineered laboratory plates, it appears in the fine details of atomic behavior. The hydrogen atom became a kind of listening device for the vacuum. Not in a dramatic science fiction sense, but in the precise scientific sense that its energy levels carried information about quantum field effects. By measuring a tiny shift, physicists could test whether their understanding of electrons, photons, and the electromagnetic field was correct. The size of the Lamb shift is small, but its meaning is large. It confirms that the vacuum cannot be ignored even in the simplest atom. It shows that the electromagnetic field is not merely present when visible light is passing through space. Its quantum nature is part of the background in which charged particles exist. An atom is not separate from the fields around it. It is one of the ways those fields and particles form stable, measurable structure. This also helps correct the everyday idea of emptiness. If empty space were truly nothing, it would have no role to play in the internal details of hydrogen. It would not shift energy levels. It would not appear in precision calculations. It would not help explain a measure difference that earlier theory missed. But the Lamb shift says otherwise. The vacuum is quiet but not irrelevant. There is something calming about this, even though the science is strange. The world does not become less real, because empty space has hidden structure. Atoms still form matter. Hydrogen still behaves like hydrogen. Light still carries energy. The difference is that the foundations are more subtle than they first appear. The stability of the ordinary world rests on quantum rules that are both delicate and extraordinarily reliable. So the Lamb shift gives another answer to the mystery of empty space. It shows that the vacuum is not just the darkness between things, it is also present in the fine structure of things. Even inside the simplest atom, where one electron and one proton form the most basic chemical element in the universe, the quiet background of quantum fields leaves a trace. Empty space does not need to be loud to be real. Sometimes it only needs to shift hydrogen by the tiniest amount. The electromagnetic field has been the main doorway into the mystery of empty space so far. It gave light a physical identity. It gave photons a quantum home. It explained why the vacuum around atoms could influence energy levels, and why apparently empty gaps between metal plates could produce tiny forces. But the electromagnetic field is only one part of the deeper modern picture. In the standard model of particle physics, the universe is not described as one field with a few particles sprinkled into it. It is described through a collection of quantum fields, each with its own particles, interactions, and rules. The standard model is the most successful theory physicists currently have for describing the known elementary particles and 3 of the 4 known fundamental interactions. It includes electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. Gravity, described by general relativity, is not part of the standard model, which is one of the reasons the full story of reality remains unfinished. Still, within its domain, the standard model is astonishingly powerful. It describes matter particles such as electrons, quarks, and neutrinos. It describes force-carrying particles such as photons, gluons, and the particles associated with the weak nuclear interaction. But in the deeper quantum field view, these particles are not the most fundamental things. They are excitations of fields. The electron is connected to the electron field. That field is not a tiny object sitting where the electron happens to be. It is part of the underlying description spread through space-time. When the electron field is excited in the right way, an electron can be observed. Remove the electron, and the field has not disappeared. It remains in its vacuum state. Quarks have their own fields as well. Quarks are the particles that make up protons and neutrons, along with many other short-lived particles produced in high-energy experiments. A proton is not a simple little ball. It contains quarks, gluons, and a restless internal structure governed by the strong nuclear interaction. The quark fields are part of the standard model's description of matter, and they help explain why atomic nuclei can exist at all. The photon field, more commonly called the electromagnetic field, gives rise to photons. Photons are the quantum particles of light and electromagnetic radiation. They're connected to everything from radio waves to visible light to X-rays. Whenever a charged particle interacts electromagnetically, the photon field is part of the story. Then there are gluon fields. Gluons are associated with the strong nuclear interaction, the force that binds quarks together inside protons and neutrons. The strong nuclear interaction is strange and powerful. It behaves very differently from electromagnetism. Instead of fading gently into simplicity at small scales, it becomes more complex as quarks are pulled apart. This is why isolated quarks are not seen drifting freely through ordinary space. They're confined inside particles such as protons and neutrons. It is as though nature allows quarks to live in groups, but does not often let them wander off alone with a tiny suitcase. The weak nuclear interaction has its own fields and force-carrying particles. This interaction is responsible for certain kinds of particle transformation, including processes involved in radioactive decay. It plays a crucial role in the nuclear reactions inside stars and in the behavior of neutrinos. The weak nuclear interaction helps explain how one kind of particle can change into another, which makes it essential for understanding both particle physics and cosmic processes. Together, these fields make the standard model far richer than the older idea of particles moving through an empty container. The background of the universe is not merely a blank stage, it is a structured physical system made from quantum fields. The fields associated with electrons, quarks, photons, gluons, neutrinos, and the weak nuclear interaction are all part of the modern picture. This is where empty space becomes especially strange. In everyday thinking, a field might seem to exist only where something is happening. A magnetic field around a magnet, an electric field around a charge, a ripple in a pond where a stone has landed. But in quantum field theory, fields are not temporary decorations added only when particles appear. They are the foundation from which particles arise. Even when a region contains no ordinary particles, the fields themselves are still present in their lowest energy states. So empty space is not empty of the electron field. It is not empty of the quark fields. It is not empty of the photon field or the gluon fields. It is not empty of the fields associated with the weak nuclear interaction. It is empty only in the sense that those fields are not excited into ordinary detectable particles in that region. That distinction is subtle, but it changes everything. The standard model has been tested most dramatically at high-energy particle accelerators, especially at CERN, the European Organization for Nuclear Research. The Large Hadron Collider near Geneva accelerates protons to enormous energies and smashes them together, allowing physicists to study the particles and interactions produced in those collisions. These experiments do not simply look for tiny objects hidden inside protons. They probe the behavior of quantum fields under extreme conditions. When new particles appear in these collisions, they are not being pulled from an ordinary empty box. Energy is being concentrated into the fields, creating excitations that can be detected as particles. The detectors record traces, energies, decay products, and patterns, and from those clues, physicists reconstruct what happened. It is a bit like listening to a cathedral bell from several streets away, and working out not only that it rang, but which bell, how hard, and what the weather was doing at the time, except with more magnets and fewer pigeons. This is why the quantum mystery of empty space cannot be separated from the standard model. The vacuum is not a simple absence beneath the world. It is the quiet state of the same fields that produce matter, light, and particle interactions. The things seen in laboratories, stars, atoms, and particle collisions are excited patterns in fields that are already woven into space-time. The older vacuum removed air. The classical field picture allowed waves and forces to cross empty regions. The quantum field picture goes deeper still. It says that the background itself has structure. Empty space is not an empty container waiting for physics to happen inside it. It is part of the physics. Among all the fields in modern physics, the Higgs field has a special kind of quiet strangeness. It is not simply another field that can ripple or produce particles. It is one of the clearest examples of how empty space can have a physical property of its own. That phrase can sound odd at first. Empty space having a property feels almost contradictory. If a region contains no ordinary matter, no dust, no gas, no light passing through it, and no detectable particles, then what is left to have any property at all? But quantum field theory does not describe the vacuum as a perfect absence. It describes it as the lowest energy state of fields, and the Higgs field makes this idea especially important, because its vacuum state is not just a quiet background. It helps shape the behavior of elementary particles themselves. The Higgs field is different from many familiar fields because it has a non-zero value throughout space. In other words, it is not switched off in the vacuum. Even in what seems like empty space, the Higgs field is present in a steady background condition. This does not mean the vacuum is full of visible stuff, or that the Higgs field is a kind of hidden mist drifting between galaxies. It means that, in the standard model of particle physics, the lowest energy state of the universe includes a Higgs field with a value that is not zero. This is one of the deepest ways in which empty space is not empty. The story of the Higgs field grew out of a problem in particle physics. Physicists needed to explain how certain elementary particles could have mass while keeping the mathematics of the standard model consistent. In the early 1960s, several physicists developed the ideas now connected with the Higgs mechanism. Peter Higgs, François Engler, Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble all contributed to this crucial theoretical development. The Higgs mechanism explains how certain elementary particles acquire mass through their interaction with the Higgs field. This is often shortened into the phrase, "The Higgs field gives particles mass," but that phrase needs careful handling. It is broadly useful, but it can also become misleading if it sounds as though the Higgs field gives mass to everything in the same simple way. Some elementary particles interact strongly with the Higgs field, and they have more mass. Others interact weakly with it, and they have less mass. Photons, the particles of light, do not acquire mass through the Higgs field, which is why they remain massless in the standard model. Electrons do interact with the Higgs field, and that interaction is connected to the electron's mass. The particles associated with the weak nuclear interaction also acquire mass through the Higgs mechanism, which is essential for explaining why the weak nuclear interaction behaves over such short distances. But most of the mass of ordinary matter does not come directly from the Higgs field. This is one of those details that matters, because it keeps the explanation honest. The atoms in a person's body are mostly made of protons and neutrons are made of quarks and gluons. The quarks themselves get their elementary masses through interaction with the Higgs field, but the quarks' masses are only a small part of the total mass of protons and neutrons. Most of that mass comes from the energy of the strong nuclear interaction, including the restless motion and field energy of quarks and gluons inside them. This is a beautiful example of how mass is not always what everyday intuition imagines. A proton is not heavy mainly because it contains a few tiny heavy lumps. Most of its mass comes from confined energy inside the proton. The strong nuclear interaction, described by quantum chromodynamics, is doing much of the work. So the Higgs field is absolutely essential, but it should not be turned into a one-size-fits-all explanation for every gram of matter. Physics, as usual, prefers to be magnificent and slightly inconvenient. Still, the Higgs field remains extraordinary, because it means the vacuum itself helps determine the basic properties of particles. A field with a non-zero value throughout empty space changes what particles are like. It affects whether certain particles have mass and how they behave. The vacuum is not just the background behind matter, it is part of the reason matter has the properties it does. For decades, the Higgs field was a theoretical idea supported by the structure of the standard model, but physicists wanted direct experimental evidence connected to it. If the Higgs field existed, then the theory predicted a particle associated with excitations of that field, the Higgs boson. A boson is a type of particle that can carry forces or arise as a field excitation, and in this case, the Higgs boson would be a detectable ripple of the Higgs field. Finding it was not easy. The Higgs boson is very short-lived. It does not linger politely in a detector waiting to be admired. It appears in high-energy collisions and then decays almost immediately into other particles. Physicists had to search for its fingerprints by studying the patterns of particles produced after collisions. That search reached its great milestone at CERN, the European Organization for Nuclear Research, using the Large Hadron Collider. In 2012, the ATLAS and CMS collaborations announced the discovery of a new particle consistent with the Higgs boson. This was one of the most important experimental achievements in modern physics. It confirmed a central part of the Standard Model and showed that the Higgs field was not merely a clever mathematical possibility. It was connected to measurable reality. The discovery did not mean everything was solved. It did not explain dark matter, quantum gravity, or why the Higgs field has exactly the value it does. It did not complete physics and allow everyone to go home early with a celebratory biscuit. But it confirmed something profound. The vacuum has structure, and that structure helps determine the properties of elementary particles. This is why the Higgs field belongs so deeply in the quantum mystery of empty space. It shows that empty space is not simply an empty container in which particles move. It is not only a stage where matter performs. The vacuum has fields. Those fields have states, and at least one of those fields, the Higgs field, has a non-zero value everywhere in the vacuum. That means the properties of matter are tied to the condition of empty space itself. A particle moving through the universe is not moving through a featureless nothing. It exists within a background of quantum fields, including the Higgs field. Its mass, its interactions, and its role in the Standard Model are shaped by that deeper structure. The vacuum is not visible. It does not glow. It does not feel solid. But it is not physically meaningless. There is something quietly astonishing about this. The most ordinary matter in the world, the matter of hands, stones, stars, and sleeping cats, depends on hidden field structures that fill even the emptiest regions of space. The universe does not need to pack empty space with objects to make it important. It only needs the vacuum itself to have the right kind of structure. And the Higgs field shows that it does. So far, the mystery of empty space has stayed mostly in the world of particles, atoms, fields, and carefully measured laboratory effects. The vacuum has shaped tiny forces between plates. It has shifted the energy levels of hydrogen. It has appeared in the structure of the Standard Model, where fields fill space-time even when no ordinary particles are present. But the question does not stop at the small scale. If empty space has quantum fields, and if those fields have vacuum states, then a larger and more unsettling question begins to appear. Does empty space itself have energy? This question leads out of the atom and into the whole universe. It links quantum field theory, which describes the smallest known scales of matter and interaction, with cosmology, which studies the origin, structure, and evolution of the universe as a whole. And this is where the vacuum becomes not only strange, but deeply unresolved. The idea that space itself might have an energy connected to it has a long history. In 1917, Albert Einstein introduced the cosmological constant into his theory of general relativity. General relativity, published in its mature form in 1915, describes gravity not as an ordinary force pulling objects through fixed space, but as the curvature of space-time caused by mass and energy. Einstein originally added the cosmological constant while trying to describe a static universe. At the time, many scientists assumed the universe as a whole was eternal and unchanging on the larger scales. But Einstein's equations naturally allowed space to expand or contract. The cosmological constant could act as an additional term that helped hold the model in balance. Later, when evidence grew that the universe is expanding, especially through the work of Edwin Hubble and others in the 1920s, Einstein's original motivation for the cosmological constant seemed unnecessary. But the idea itself did not disappear. Physics has a way of putting old ideas in a drawer, then pulling them out decades later with a small note saying, actually, this may still be important. In modern cosmology, the cosmological constant can be understood as an energy density associated with space itself. That means it is not energy stored in stars, gas, radiation, or ordinary matter. It is something linked to space-time at the largest scale, a kind of background contribution that does not thin out in the same way matter does as the universe expands. This is a strange idea. If a box expands, the ordinary matter inside it becomes more spread out. Galaxies move farther apart. Gas becomes more dilute. Radiation gets stretched to longer wavelengths. But a cosmological constant behaves differently. Its energy density remains constant as space expands, at least in the simplest model. This means that as more space appears in the expanding universe, the total amount of this space-associated energy also increases. That sentence can sit quietly in the mind for a moment, because it is one of those places where cosmology becomes very calm and very odd at the same time. The physical interpretation remains challenging. The cosmological constant is mathematically simple, but its deeper meaning is not simple at all. Is it truly vacuum energy? Is it a property of space-time? Is it connected to quantum fields? Is it pointing towards something deeper that has not yet been understood? These questions remain open. The modern urgency around this idea came from observations in the late 1990s. Two research groups, the Supernova Cosmology Project and the High-Z Supernova Search Team, studied distant Type 1 supernovae. These supernovae are extremely bright stellar explosions that can be used as distance indicators because their intrinsic brightness can be estimated in a reliable way after careful correction. By comparing how bright they appear with how far away they are, astronomers can trace the expansion history of the universe. The expectation had been that gravity should slow the expansion down over time. Matter attracts matter. Galaxies pull on one another. Even if the universe was expanding, it seemed reasonable to expect that expansion to be decelerating. But the distant supernovae suggested something surprising. The expansion of the universe was not slowing down in the expected way. It was accelerating. This discovery was later recognized with the Nobel Prize awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees. Their work helped establish that something is driving the accelerated expansion of the universe, that something is called dark energy. Dark energy is not dark because it is shadowy or sinister. It is dark because its nature is unknown. It does not appear to be ordinary matter. It does not shine like stars. It does not clump strongly like galaxies. It is inferred from its effect on cosmic expansion. The simplest current model of dark energy is the cosmological constant, a constant energy density associated with space itself. This brings the vacuum mystery into the largest possible arena. If quantum fields have vacuum energy, and if empty space on cosmic scales behaves as though it has an energy density, perhaps these ideas are connected. That possibility is natural, but it leads straight into one of the most difficult problems in modern physics. The observed value associated with dark energy is extremely small compared with many straightforward theoretical estimates of vacuum energy from quantum field theory. The problem is not a small mismatch, like a recipe asking for slightly too much flour. It is enormous. Theoretical expectations and observed cosmic behavior do not naturally line up. This is known as the vacuum energy problem, and it is closely related to the cosmological constant problem. It reveals a deep tension between two of the most successful frameworks in science. Quantum field theory describes particles and fields with extraordinary precision. General relativity describes gravity and the large-scale structure of the universe with astonishing success. But when the energy of the quantum vacuum is brought into the gravitational story, something does not yet fit. That is why vacuum energy is so important. It is not only a question about tiny fluctuations or laboratory plates. It may be connected to the fate of the entire universe. The same idea of empty space, once treated as a simple absence, now touches the expansion of cosmic space itself. Empty space may help atoms behave as they do. It may shape tiny forces, it may give particles some of their basic properties, and on the larger scales, it may be linked to the acceleration of the universe. The mystery is not that empty space is silent. The mystery is that, when physics listens closely enough, the silence seems to weigh on the cosmos. The vacuum energy problem is one of those places where modern physics becomes both impressive and deeply unsettled. It is not a mystery born from ignorance. It is not a gap where no one has any idea what is going on. It is almost the opposite. The problem exists because two extremely successful ways of describing nature seem to point toward answers that do not comfortably agree. One side of the problem comes from quantum field theory. This is the framework that treats particles as excitations of fields spread through space-time. It describes electrons, photons, quarks, gluons, and the other particles of the Standard Model with extraordinary power. It explains the Lamb shift. It explains the electron's magnetic moment with astonishing precision. It gives physicists a detailed language for particle creation, particle interactions, and the subtle behavior of the vacuum. The other side comes from general relativity. This is Albert Einstein's theory of gravity, where mass and energy shape space-time, and space-time guides the motion of matter and light. General relativity describes black holes, gravitational waves, the bending of light around massive objects, and the expansion of the universe. It has also survived many demanding tests. The trouble begins when the vacuum is asked to belong to both stories at once. In quantum field theory, every field has a vacuum state, its lowest energy state. That state is not classical nothingness. It is not a perfectly empty absence. Fields in their vacuum state can still contribute to calculations, and they can still have measurable effects. The electromagnetic field, for example, helps explain tiny shifts in atomic energy levels and delicate forces such as the Casimir effect. So it is natural to ask whether the vacuum energy of all these fields should also contribute to gravity. In general relativity, energy is not merely something that sits inside the universe. Energy helps shape space-time. Matter, radiation, pressure, and energy density all play roles in the gravitational behavior of the cosmos. If empty space has energy, then that energy should matter gravitationally. It should affect the expansion of the universe. And, in a broad observational sense, something like that does appear to be happening. The universe's expansion is accelerating. The simplest model for this acceleration is the cosmological constant, which can be understood as an energy density associated with space itself. This effective energy density is very small, but it is not zero. It seems to act across the whole observable universe, quietly influencing cosmic expansion. So far, that may sound like a difficult but promising connection. Quantum field theory says the vacuum has energy. Cosmology says empty space may have an energy density linked to accelerated expansion. Perhaps the two ideas fit neatly together. Unfortunately, they do not fit neatly together. When physicists make simple estimates of vacuum energy using quantum field theory, the expected value is vastly larger than the value inferred from cosmic acceleration. Depending on exactly how the estimate is made, the mismatch can be described as roughly 120 orders of magnitude. An order of magnitude means a factor of 10, so a mismatch of that scale is not a small disagreement. It is not like expecting a cup of tea and receiving a slightly larger mug. It is more like expecting a small teacup and discovering that the calculation has ordered an entire ocean with a biscuit balanced on top for morale. This is why the cosmological constant problem is sometimes called the worst prediction in physics. The phrase is a little playful, but the problem behind it is serious. It does not mean quantum field theory is useless. Quite the opposite. Quantum field theory is one of the most successful frameworks in all of science. It does not mean general relativity is failing in everyday gravitational test either. General relativity remains extraordinarily successful. The difficulty is that, when the vacuum energy from quantum fields is placed into the gravitational setting of the whole universe, the result seems wildly wrong unless something cancels, suppresses, or reinterprets it in a way that is not yet understood. This is not merely a mathematical inconvenience, it is a conceptual wound between two great theories. Quantum field theory is built for the small scale, where particles and fields obey quantum rules. General relativity is built for the large scale, where space-time curves and evolves. Both theories have deep experimental support, but they were not originally built as one unified theory. The cosmological constant problem reveals that the vacuum sits directly at their border. Empty space is where the small-scale quantum rules and the large-scale gravitational rules are forced to speak to each other. At the moment, their conversation is not going smoothly. Steven Weinberg wrote influentially about the cosmological constant problem and helped emphasize its importance in theoretical physics. He showed why the problem is not easy to dismiss, and why simply setting the cosmological constant to zero does not solve the issue once observations suggest a small but non-zero value. The question becomes sharper. Why is the observed value so tiny compared with naive quantum estimates, and yet not exactly zero? There are many possible ideas, but no final answer. Some approaches suggest there may be unknown symmetries that cancel most of the vacuum energy. Supersymmetry, a proposed symmetry between matter particles and force-carrying particles, can reduce some vacuum energy contributions in idealized forms, but it has not been confirmed experimentally in the simple ways many physicists once hoped. Other ideas involve dynamic dark energy, where the cause of cosmic acceleration might change over time rather than being a true constant. Some physicists explore anthropic reasoning in a multiverse context, suggesting that observers would only arise in regions where the cosmological constant allows galaxies to form. That idea remains debated and is not a settled physical explanation. There are also approaches that question whether the vacuum energy calculated in quantum field theory should gravitate in the straightforward way assumed by the simplest argument. Others suggest that a full theory of quantum gravity may change the problem completely. But because no complete, experimentally confirmed theory of quantum gravity yet exists, the mystery remains open. What makes this puzzle so fascinating is that it does not come from a lack of precision. The theories are precise, the observations are powerful, the supernova measurements, cosmic microwave background studies, galaxy surveys, and other cosmological evidence all point toward a universe whose expansion is accelerating. Quantum field theory continues to work beautifully in particle physics. The problem is that the bridge between them does not yet hold. So empty space becomes mysterious in a very particular way. It is not mysterious because science has nothing to say about it. Science has a great deal to say. It can describe the quantum vacuum, field fluctuations, particle interactions, atomic shifts, and cosmic acceleration. It can measure tiny effects in laboratories and vast patterns across the sky. The mystery comes from the fact that these pieces do not yet form one complete picture. Empty space, then, is not an empty absence at the edge of understanding. It is right at the center of understanding. It is where the most successful theories begin to press against their limits, and that may be the deepest reason the vacuum feels so strange. It is quiet enough to look like nothing, but important enough to reveal that something profound still does not fit. Empty space is already strange when it's imagined far from everything, stretched between stars, galaxies, and drifting clouds of gas. But it becomes stranger still near a black hole, where the vacuum is no longer sitting inside calm, almost flat space-time. It is placed beside one of the most extreme gravitational environments in the universe. A black hole is not simply a heavy object with a strong pull. like a cosmic version of a very demanding magnet. In modern physics, gravity is not treated as an ordinary force acting through a fixed background. Albert Einstein's theory of general relativity, published in its mature form in 1915, describes gravity as the curvature of space-time itself. Matter and energy tell space-time how to curve, and curved space-time tells matter and light how to move. This changed the meaning of gravity completely. Instead of imagining planets, stars, and light beams moving through an invisible stage while gravity tugs on them from a distance, general relativity says the stage itself is shaped. Space and time are not passive scenery. They are part of the physical system. Around Earth, that curvature is gentle. Around the Sun, it is stronger, strong enough to bend passing starlight by a measurable amount. Near a black hole, space-time becomes so curved that a boundary called the event horizon forms. The event horizon is not a solid surface. A falling object would not hit it like a wall. It is a causal boundary, a region beyond which light cannot escape to the outside universe. Once something crosses the event horizon, all future paths through space-time lead inward. Not because the object has chosen poorly, although that would be understandable, but because space-time itself is arranged that way. This already makes empty space difficult to think about. The vacuum is no longer a quiet state inside a simple background. The background has become curved, and in extreme cases it contains horizons. Quantum field theory was first developed most successfully in the setting of special relativity, where space-time can be treated as flat. But black holes require physicists to ask what quantum fields do when space-time itself is strongly curved. This question led to one of the most remarkable predictions in 20th century physics. In the 1970s, Stephen Hawking studied quantum field theory in curved space-time and found that black holes should not be completely black. They should emit thermal radiation, now called Hawking radiation. This was astonishing because black holes had been understood as objects from which nothing, not even light, could escape once it passed the event horizon. Yet Hawking's calculation suggested that black holes can slowly lose energy and, over immense timescales, gradually evaporate. Hawking radiation is often explained through a simple picture. Pairs of particles appear near the event horizon, one falls in and the other escapes. This image can be useful as a first sketch, but it should not be taken too literally. Hawking radiation is not simply ordinary particles crawling out from inside the event horizon, as if the black hole has accidentally left a back door open. Nothing escapes from inside the event horizon in the usual sense. The deeper explanation involves quantum fields in curved space-time, especially near a horizon. What one observer describes as the vacuum may not match what another observer detects as particles. The presence of the event horizon changes how the field modes are defined across space-time, and the result is that an outside observer can describe the black hole as emitting a faint thermal glow. The radiation is connected to the black hole's mass, gravity, and horizon, not to a simple mechanical spraying of particles from within. For ordinary astrophysical black holes, Hawking radiation is incredibly weak. A black hole with the mass of a star would be far colder than the cosmic microwave background radiation that fills the universe. Detecting its Hawking radiation directly would be extraordinarily difficult. But the importance of the prediction does not depend on it being easy to measure from a telescope. Its power lies in what it reveals about the meeting point of quantum theory, gravity, and thermodynamics. Thermodynamics enters through the work of Jacob Bekenstein. Before Hawking's radiation calculation, Bekenstein argued that black holes should have entropy. Entropy is often described as a measure connected to disorder, but more carefully it relates to the number of microscopic ways a physical system can be arranged while appearing the same at a larger scale. Bekenstein proposed that black hole entropy is connected to the area of the event horizon, not the volume inside it. That was a startling idea. In ordinary objects, entropy is usually associated with the matter and energy making up the object, but a black hole hides its interior from the outside universe. Bekenstein's work suggested that the horizon itself carries deep information about the black hole's physical state. Hawking's later result gave the idea even more force, because thermal radiation implies temperature, and temperature belongs naturally with entropy and thermodynamics. Black holes therefore connect some of the deepest concepts in physics: general relativity, quantum field theory, thermodynamics, entropy, and information. They're not just astronomical curiosities. They're places where the rules of nature overlap in ways that are still not fully understood. And once again, empty space sits at the centre of the puzzle. Near a black hole, the vacuum is not easy to define in one simple universal way. In flat space-time, physicists can often identify a natural vacuum state for a quantum field. Near a black hole, especially with an event horizon involved, the meaning of no particles can depend on the observer and the space-time geometry. A freely falling observer and a distant observer may not describe the field in exactly the same way. This does not mean reality becomes arbitrary. It means the concept of particles is more subtle in quantum field theory than in everyday thinking. Particles are excitations of fields, and how those excitations are defined can depend on the structure of space-time and the motion of the observer. The vacuum is not always a simple, universal emptiness that everyone agrees on without qualification. This is why black holes make the quantum mystery of empty space deeper. The vacuum was already strange when fields were placed in ordinary empty regions. It became measurable through effects like the Lamb shift and the Casimir effect. It became cosmological through vacuum energy and dark energy. But near black holes, the vacuum becomes entangled with gravity, horizons, entropy, and information. Empty space near a black hole is not a silent background beside a dramatic object. It is part of the drama itself. It shows that the vacuum is not just what remains when matter is removed. It is a quantum state shaped by fields, observers, and space-time. And when space-time curves strongly enough to form a horizon, even the meaning of emptiness begins to bend. The vacuum has already become far stranger than ordinary emptiness. It can shift atomic energy levels, influence tiny forces between plates, appear in discussions of cosmic acceleration, and become difficult to define near black hole horizons. But there is another layer of strangeness, quieter and more subtle, where empty space depends not only on what is present, but also on how an observer is moving. This idea appears in the Unruh effect. The Unruh effect is a theoretical prediction in quantum field theory and relativity. It says that what looks like the vacuum to one observer may not look like the vacuum to another observer if their motion is different in the right way. More specifically, an observer moving at constant velocity through empty space may describe a quantum field as being in its vacuum state, while an observer accelerating through that same region may perceive something like a faint thermal bath. The effect is named after William Unruh, who described it in the 1970s. It belongs to the same broad family of ideas as Hawking radiation, because both involve quantum fields, horizons, and the fact that particles are not always as straightforward as everyday intuition suggests. The Unruh effect does not require a black hole, but it does show that acceleration can change how the vacuum is experienced. This can sound deeply unsettling at first. Empty space is supposed to be empty. Surely either particles are there or they are not. Surely the vacuum cannot depend on who is looking at it. But in quantum field theory, particles are excitations of fields, and the way those excitations are defined can depend on the observer's motion and the structure of space-time. The field itself is the deeper object. The particle description is sometimes more observer-dependent than the familiar image of tiny objects moving through space. An inertial observer is one who is not accelerating. In simple terms, this means an observer drifting freely, not being pushed, pulled, fired by rockets, or otherwise persuaded into changing motion by a deeply enthusiastic engine. For such an observer in flat spacetime, a field can be described as being in its vacuum state. No real particles are detected, but an accelerating observer may not agree. According to the Unruh effect, that accelerating observer can detect a temperature associated with the vacuum. The faster the acceleration, the higher the temperature. The vacuum for one observer becomes, for the accelerating observer, something that resembles warm radiation. This is not an everyday effect. The acceleration needed to produce even a tiny noticeable temperature is enormous. It is far beyond ordinary experiences of cars, trains, lifts, or aircraft. A person speeding up in a car is not going to suddenly discover the vacuum glowing warmly around them, which is probably for the best, because driving is already distracting enough. The Unruh temperature for ordinary accelerations would be unimaginably small. Detecting the effect directly is extremely difficult, and it remains a subtle theoretical prediction rather than a routine laboratory observation. Still, the idea matters because it reveals something profound about empty space. It shows that the vacuum is not always a simple, universal nothing that every observer must describe in exactly the same way. In quantum field theory, the notion of particles can depend on how the field is being observed. An accelerating detector may respond as though particles are present, even where an inertial observer describes the field as vacuum. There is a gentle comparison here with special relativity, though it should not be pushed too far. In special relativity, motion affects measurements of time and space. Two observers moving differently can disagree about lengths, time intervals, and whether distant events happen at the same time. That does not mean reality is random or unreal. It means space and time are not absolute in the old Newtonian sense. Measurements depend on the observer's state of motion, while the deeper laws remain consistent. The Unruh effect suggests something similar in spirit, but in the language of quantum fields. Different observers may not define the particle content of a field in exactly the same way. One observer's vacuum can be another observer's thermal bath if one observer is accelerating strongly enough. The deeper physical framework remains coherent, but the ordinary idea of empty becomes less simple. This is why the effect is often discussed alongside black holes and horizons. An accelerating observer in flat spacetime has a kind of horizon, called a Rindler horizon, beyond which certain events cannot influence them. This is not the same thing as a black hole event horizon, but there is a mathematical relationship in how quantum fields behave near horizons. Hawking radiation and the Unruh effect both show that horizons, motion, and quantum fields can make the vacuum behave in surprising ways. The Unruh effect is difficult to observe directly, but related ideas appear throughout theoretical physics. They help physicists think about black hole radiation, quantum fields in curved space-time, observer-dependent particle definitions, and the deep connection between acceleration, temperature, and horizons. Even if the effect itself is subtle, it acts like a small window into a much larger structure. For the mystery of empty space, its meaning is quietly powerful. Empty space is not only strange because it contains quantum fields. It is not only strange because those fields have lowest energy states, fluctuations, and measurable consequences. It is also strange because the meaning of no particles is not always absolute. What counts as vacuum can depend on the observer's motion. That does not make the vacuum imaginary. It makes it more refined. It means the simple picture of empty space as a fixed container with either particles inside it or no particles inside it is not deep enough. Quantum field theory asks for something subtler. The field is primary. The observer's motion matters. The particle description is sometimes a matter of how the field is sliced, measured, and experienced. So empty space is not merely a location where nothing happens. It is a quantum state whose meaning can depend on motion, acceleration, and the structure of space-time. The vacuum is quieter than matter, quieter than radiation, quieter than starlight crossing the dark. But even that quietness is not seen in exactly the same way by everyone. The vacuum has so far appeared as the lowest energy state of quantum fields. It has shaped tiny forces, shifted atoms, filled the standard model with hidden structure, and become strangely observer-dependent when motion, horizons, and gravity enter the picture. But there is another question, quieter, and perhaps even more unsettling. Is the vacuum we live in truly stable? At first, that question sounds almost too strange to be meaningful. Empty space feels like the most basic possible background. It does not seem like the kind of thing that could have a condition, a history, or a future. A star can burn out. A particle can decay. A building can become unstable if someone has made unfortunate decisions with the foundations. But empty space itself seems as though it should simply be what it is. Quantum field theory suggests a more subtle possibility. A false vacuum is a state that appears stable, but may not be the absolute lowest energy state possible. It is not unstable in the ordinary sense of wobbling visibly or falling apart at any moment. It may last for an unimaginably long time. It may behave perfectly normally across all known observations, but if there is a deeper, lower energy vacuum state available, then the current vacuum could be only metastable. Metastable means stable for a very long time, but not absolutely stable in the deepest theoretical sense. A helpful loose image is a ball resting in a shallow valley on a hillside. It may sit there peacefully for ages. Small disturbances will not move it far. From nearby it looks settled. But if there is a deeper valley elsewhere, then the ball is not in the lowest possible place overall. It is stable locally, but not globally. The comparison is imperfect, because the vacuum is not a literal ball, and the Higgs field is not a countryside with suspiciously mathematical hills, but it gives the right flavour. In quantum field theory, the stability of the vacuum depends on the energy landscape of fields. The Higgs field is especially important here. The Higgs field has a non-zero value throughout empty space, and that value helps determine the masses of certain elementary particles. But the Higgs field also has an energy landscape, meaning different possible values of the field correspond to different energy states. The question is whether the value of the Higgs field in our universe sits in the absolute lowest energy state, or whether it sits in a state that is only temporarily secure. This is where discussions of vacuum decay begin. If the current vacuum were false, then in principle it could transition to a lower energy state through quantum tunneling. Quantum tunneling is a real feature of quantum physics, where a system can pass through a barrier that would be forbidden in classical physics. In field theory, this idea can be extended to the possibility of a false vacuum changing into a true vacuum. Sidney Coleman made important contributions to the theory of false vacuum decay, especially in the context of quantum tunneling in fields. His work helped physicists understand how a transition from a false vacuum to a lower energy vacuum might be described mathematically. Later theoretical discussions developed these ideas further, connecting them to particle physics, cosmology, and the early universe. This sounds dramatic, so it needs to be handled calmly. Vacuum decay is theoretical. It's not a prediction that the universe is about to collapse, unravel, or suddenly redecorate itself in a less convenient style. Current physics does not suggest an imminent cosmic disaster. If our vacuum is metastable, its expected lifetime could be vastly longer than the current age of the universe. The numbers involved are so enormous that everyday anxiety is not really invited to the meeting. The reason physicists take the question seriously is not because it is sensational, but because it may reveal something important about the Higgs field, the Standard Model, and the deep structure of empty space. Measurements of the Higgs boson and the top quark are especially relevant. The Higgs boson was discovered at CERN in 2012 by the ATLAS and CMS collaborations at the Large Hadron Collider. Its measured mass helped physicists study the shape of the Higgs field's energy landscape. The top quark matters because it interacts strongly with the Higgs field, and its mass has a significant influence on calculations of vacuum stability. Current measurements suggest that the universe may be near a boundary between stable and metastable behavior, but uncertainties remain. The exact conclusion depends on precise values of the Higgs boson mass, the top quark mass, and the details of the Standard Model calculations. It also depends on whether unknown physics beyond the Standard Model exist at higher energies. If new particles or interactions exist, they could change the stability picture. So the honest answer is not simple. The vacuum might be absolutely stable. It might be metastable with a lifetime so long that, for all practical cosmic purposes, it is stable. Or the current calculations may be incomplete because the Standard Model is not the final theory. Dark matter, neutrino masses, and gravity already suggest that there is more to physics than the Standard Model alone describes. This is what makes the false vacuum idea so fascinating. It shows that empty space is not merely a passive emptiness, it has a state. That state has properties. Those properties depend on fields, and those fields may have different possible arrangements, some lower in energy than others. The quantum mystery of empty space is therefore not only about what the vacuum contains, or what it does, or how it affects particles and forces. It is also about whether the vacuum we know is final. The quiet space between galaxies may be sitting in the deepest possible state of nature, or it may be resting in a long-lived state that only appears final from inside it. Either way, the ordinary darkness of empty space becomes something far richer than a blank background. It becomes a question about the stability of reality itself. Empty space remains a mystery because it is not empty in the way ordinary language first suggests. It is not simply a blank gap between stars. It is not only the absence of air, dust, atoms, light, and visible motion. And it is not the same as absolute nothingness. The more carefully physics has examined empty space, the more it has become clear that emptiness is not a simple lack of things, but a physical condition with layers of meaning. The first layer was the classical vacuum. This was the idea of a region where ordinary matter had been removed. No air molecules, no gas pressure, no visible substance. Experiments with barometers, pumps, and sealed chambers showed that this kind of emptiness could be made, measured, and studied. The vacuum stopped being only a philosophical argument and became something that belonged in laboratories, but it still seemed at first like a cleaned-out container, useful, measurable, but mostly passive. Then fields changed the picture. Michael Faraday's lines of force and James Clerk Maxwell's electromagnetic theory revealed that space could hold invisible structure even when no matter was present. Electric and magnetic fields could stretch through apparently empty regions. Light itself became understood as an electromagnetic wave, able to cross the vacuum without air to carry it. Empty space was no longer merely empty of matter. It could contain fields, waves, and energy moving through darkness. Then quantum physics made the picture stranger again. Max Planck's work on blackbody radiation and Albert Einstein's explanation of the photoelectric effect showed that energy and light could behave in discrete quantum ways. Light was not only a smooth electromagnetic wave, it could also arrive in particle-like packets called photons. Niels Bohr's atomic model showed that atoms absorb and emit specific colours of light because electrons occupy particular energy levels. The universe had begun to reveal that the deep behavior of matter and radiation was not smooth, continuous and classical. Soon, even particles stopped looking like simple particles. Louis de Broglie proposed that matter has wave-like properties. Electron diffraction experiments by Clinton Davison, Lester Germer, and George Paget Thompson showed that electrons could produce interference patterns. Erwin Schrödinger's wave mechanics and Werner Heisenberg's matrix mechanics gave physics new mathematical languages for quantum behavior. Heisenberg's uncertainty principle showed that certain properties, such as position and momentum, cannot both be defined with unlimited precision at the same time. That uncertainty did not only affect particles, it also shaped the meaning of fields. Quantum field theory brought the story together by treating particles as excitations of underlying fields that fill space-time. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks, gluons, neutrinos, and other particles belong to their own fields within the standard model of particle physics. In this view, empty space is not a place where the fields have vanished. It is the lowest energy state of those fields. That is the quantum vacuum. It is a physical state, not an absolute absence. It is shaped by quantum uncertainty, by relativity, and by the structure of the standard model. It is quieter than a region filled with particles, but it is not the same as non-existence. The fields remain, even when their ordinary particle excitations are not present. This is not just a poetic idea. It has measurable consequences. Quantum electrodynamics, the quantum field theory of the electromagnetic interaction, has been tested with extraordinary precision. It helps explain the electron's magnetic moment, the Lamb shift in hydrogen, and other subtle effects. The Lamb shift showed that the energy levels of atoms are influenced by interactions between electrons and the quantum electromagnetic field. The Casimir effect showed that closely spaced conducting plates can feel a tiny force because the allowed electromagnetic field modes between them differ from those outside them. The Higgs field added another deep layer. Unlike many fields, the Higgs field has a non-zero value throughout the vacuum. It is not switched off in empty space. Through the Higgs mechanism, developed by Peter Higgs, Francois Engler, Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble, certain elementary particles acquire mass through interaction with this field. The discovery of the Higgs boson at CERN in 2012 by the ATLAS and CMS collaborations confirmed a central part of this picture. Empty space, in this sense, helps determine the properties of matter itself. These parts of the story are well established. Quantum electrodynamics is extraordinarily accurate. Field excitations are central to modern particle physics. Precision measurements support the theory again and again. The Higgs boson has been discovered. The standard model works remarkably well across a vast range of experiments, even though it is not the final theory of everything. But empty space remains mysterious because the deepest pieces still do not fit. The cosmological constant problem is one of the clearest examples. Quantum field theory suggests that vacuum energy should contribute to gravity. Cosmological observations suggest that the energy density associated with cosmic acceleration is extremely small. The mismatch between simple theoretical estimates and observed dark energy is enormous, sometimes described as roughly 120 orders of magnitude. This is not a small accounting error. It is a sign that quantum field theory and general relativity do not yet form one complete story. Quantum gravity remains unresolved. Black holes show why the problem matters. Stephen Hawking's work on black hole radiation, Jacob Bekenstein's work on black hole entropy, and later studies of information and horizons all suggest that space-time, thermodynamics, and quantum theory are connected in ways not yet fully understood. Near a black hole, Even the idea of the vacuum becomes subtle, because what counts as empty can depend on observers, horizons, and curved space-time. The false vacuum adds another quiet uncertainty. The Higgs field may sit in an absolutely stable state, or it may sit in a metastable state that only appears final from within the universe. Current measurements of the Higgs boson and top quark suggest that the question is delicate, with uncertainties still remaining. This does not imply imminent danger. It simply shows that the state of empty space may itself be a subject of deep physical inquiry. Future progress may come from many directions. Particle accelerators may reveal physics beyond the standard model. Gravitational wave astronomy may provide new clues about black holes and the behavior of space-time. Cosmological surveys may refine the nature of dark energy. Quantum technologies may test delicate vacuum effects with increasing precision. Theoretical approaches such as string theory and loop quantum gravity may help physicists search for a deeper connection between quantum fields and space-time itself. So the quantum mystery of empty space is not that science has found nothing, it is that science has found fields, vacuum states, fluctuations, forces, energy shifts, particle masses, cosmic acceleration, horizons, entropy, and unanswered questions, all gathered under the name of emptiness. The quietest places in the universe may not be empty pauses between important things. They may be where some of the most important physics is hiding in plain sight. Empty space looks like nothing. But in modern physics, it may be one of the richest ideas ever discovered. The quantum mystery of empty space is that it is not really a simple absence. It is not merely a dark gap where matter has been removed. It is not just the silence between stars or the clean interior of a vacuum chamber or the enormous blackness stretching between galaxies. In modern physics, empty space is better understood as the lowest energy state of quantum fields that fill space-time. It is quiet, but not nothing. It is empty of ordinary particles, but not empty of the fields from which particles arise. The journey began with the old question of whether true nothingness can exist. Early vacuum experiments showed that air could be removed and pressure could be measured. Classical fields then revealed that space could contain invisible electric and magnetic influences, even without ordinary matter. Planck and Einstein helped open the quantum world, where energy came in discrete packets and light itself could behave in particle-like ways. Quantum mechanics showed that matter was not made of tiny objects following perfectly certain paths, and quantum field theory brought the deeper picture into focus. Particles are excitations of fields, and the vacuum is the quiet state beneath them. From there, empty space became even more subtle. Zero-point energy showed that the lowest energy state of a quantum system does not have to mean perfect classical stillness. Vacuum fluctuations revealed that quantum fields cannot be assigned perfectly fixed values everywhere. The Casimir effect showed that the vacuum can contribute to a tiny force between closely spaced surfaces. The Lamb shift showed that the quantum electromagnetic field can alter the energy levels of hydrogen. The standard model turned empty space into a structured background of fields, and the Higgs field showed that the vacuum can help determine the properties of matter itself. Then the mystery widened to the whole universe. Dark energy and the cosmological constant raised the possibility that empty space is connected to cosmic acceleration. Black holes showed that the vacuum becomes especially strange when quantum fields meet curved space-time. The Unruh effect suggested that what counts as empty may depend on motion. The false vacuum raised the quiet question of whether the state of empty space is ultimately stable or only long-lived. None of this means the vacuum is magic. It is not a mystical substance, and it is not a source of easy energy waiting to be harvested. It is a precise scientific concept, supported by real measurements, powerful theories, and careful limits. Modern physics understands many effects of empty space extremely well, yet the deepest questions of vacuum energy, gravity, and the cosmological constant remain unresolved. So between the stars the darkness may look completely still, not because nothing is there, but because the deepest activity of nature is usually hidden beneath the level of ordinary sight,